these are going to be our notes on how derivatives affect the shape of a graph. So we start with a question that we already know how to answer, but we'll take a look. Given the graph of f of x, draw the graph of its derivative. So here we have a function, and we have already worked with problems like these, where we examine the function and we say, okay, over here on the left, we know that, notice that the slope of the tangent line is negative. It turns to 0, then it goes positive, 0 again, negative, 0, positive. So traditionally what we did was we said, okay, it's going to be 0 right about here, and then we would start marking our graph and say, all right, it's going to be 0 right about there. It's going to be 0 again here, and it's going to be 0 again here. And that on this side of the 0, your derivative ends up being negative. It then switches to positive, and then back to negative, and then finally it ends up going positive. And this is a very rough sketch of what this is going to end up looking like. For example, I only drew the positive part of the derivative here to go up this high. Well, does it really go that high, or could it possibly go this high? To answer questions like that, we're going to have to do a little bit more thorough examination of these kinds of questions. But what we do want to take a look at is we're going to try to establish a relationship between the original function and its derivative. And if you notice here, where your derivative is negative, so that's from negative infinity up to whatever value this takes on. Your derivative is negative. Look at your original function. Is it increasing or is it decreasing? Notice it's decreasing. And here, where your derivative is positive, meaning it's above the x-axis, the original function is increasing. And notice that stays consistent for the entire graph. Turns out that is the relationship between a derivative and the original function. And that's what we call the increasing and decreasing test. If your derivative is greater than 0, remember that just means positive, on a specific interval, then your original function f is increasing on that interval. And if your derivative is less than 0, meaning it's negative on that interval, then f is decreasing on that interval. Find where the function f of x equals 3x to the fourth minus 4x cubed minus 12x squared plus 5 is increasing and decreasing. Okay? So we're going to take a look at where it's increasing or decreasing by examining the sign of the first derivative. If the first derivative is positive, then this function should be increasing. If the first derivative is negative, then this function should be decreasing. So if we want to know where the derivative is positive and negative, the first thing we need to do is actually find the derivative. So the good news is this is a nice polynomial, 12x cubed minus 12x squared minus 24x. Okay, so that's our derivative. We're going to figure out where this polynomial is positive and where it's negative. So we're going to need to set it equal to 0. And when we do that, we're going to need to factor out what's common to all three terms. So we're going to get 12x out, and we'll be left with x squared minus x minus 2, and set that equal to 0. And that quadratic does factor, so we'll get 12x times x plus 1 times x minus 2, and that's going to be equal to 0. So the polynomial is equal to 0 at x equals 0, x equals negative 1, and x equals 2. So that's where it's equal to 0. I need those three on a number line. So there's negative 1, 0, and 2. And what we need to do is figure out whether the derivative is positive or negative on each of those intervals in between those numbers. So we look negative infinity to negative 1, negative 1 to 0, 0 to 2, and 2 to infinity. So we need to pick test values inside each interval. So let's say here we test x equals negative 2, here we can test x equals negative 1/2, here we can test x equals 1, here we can test x equals 3. These are by no means the only test values, they're just ones that are in the appropriate interval. So if we plug negative 2 in, and again I'm going to be examining what it's doing to the factored form of my derivative. It's a little bit easier than plugging it all the way back in to this non-factored version because the calculations are easier. Believe it or not, I don't actually care about the numerical value of the result of plugging -2 into this derivative. I mean, I don't care whether it's -5 or -6 or 5 or 6. What I care is what sign does it end up being. So if you plug it into the factored form, it's much easier to quickly figure out if it's positive or negative. Because, for example, if you plug -2 into our first factor, you're going to get a negative number. Notice I don't care what the negative number is. I just care it's a negative number. When you plug -2 into x plus 1, it comes out negative. And when you plug -2 into x minus 2, it also comes out negative. So what you end up with is a positive times a negative for negative. Same thing when we plug in -1/2. If we were to plug it back into the original derivative that isn't factored, we would have a lot more calculations to do. We'd be cubing a fraction, we'd be squaring a fraction, and while that's not incorrect to do, it's just not the most efficient way to deal with this problem. If we put -1 into the first factor, 12x, it's going to come out negative. If we put it into x plus 1, -1/2 plus 1 is a positive number. And then -1/2 minus 2 is a negative number. So we end up with a positive overall. I'll move these down here. For x equals 1, we'll get a positive times a negative, so that'll end up being negative. And then for x equals 3, we'll get a positive times a positive times a positive. So that's going to give me positive values overall. Notice they do alternate. They go negative, positive, negative, positive. Please do not assume that that's going to happen for every problem. I won't lie to you, it's common to have it alternate like that, but it by no means occurs in every one of these problems. So you do want to make sure that you're actually checking. So the conclusion we've come up with is that our derivative is negative from -infinity to -1 and from 0 to 2. Well, on those intervals, if your derivative is negative, that means that your original function f is decreasing. So f is going to be decreasing on those two particular intervals. So that's going to be -infinity to -1, and again on 0 to 2. We notice that our derivative is going to be positive on -1 to 0 and 2 to infinity. Well, if your first derivative is positive, that tells you that your original function is increasing on those two intervals. So f is increasing on -1 to 0 and again on 2 to infinity. So notice you already know everywhere that your function is increasing and decreasing just based on looking at its first derivative. Which brings us to the first derivative test. Now the first derivative test says, suppose that c is a critical number of a continuous function f. So again, remember what critical numbers are. Critical numbers are numbers in the domain of your function such that your derivative at that number is equal to 0 or your derivative at that number doesn't exist. So assuming that you have found these critical numbers of your function, if you take a look, if your derivative changes from positive to negative at a critical value, then f has a local maximum at that critical number. If your derivative changes from negative to positive at the critical number, then f has a local minimum at that critical number. And if your derivative does not change sign at your critical number, then it doesn't have a local max or a local min there. Now that should kind of make sense. I mean, A is saying that your derivative changes from positive to negative. Well, remember what we just decided. If your derivative is positive, that means that f is increasing. If your derivative is negative, that means that f is decreasing. Well, that means if your first derivative goes from positive to negative, your original function changes from increasing to decreasing. So of course, what are you going to pick up right here? You're going to pick up a local max. In B, your derivative goes from negative to positive, which says that your original function goes from decreasing to increasing. So sure enough, you're going to pick up a local minimum. And then if your derivative does not change sign at C, it means you don't have a local max or a local min. If you remember, when we discussed critical numbers previously, what we had said was that those identify the potential local maxes and local minimums, not the actual ones. But we never really gave you a way at that time to determine, well, which ones are potential local maxes and local mins versus actual local maxes and local mins. This is how you do that. Once you find the critical numbers, you test the first derivative on either side. And if you get a change from a positive to a negative at the critical number, you've got a local max. If it changes from negative to positive, you've got a local min. And if your first derivative doesn't change sign at all, then it's not an actual local maximum or local minimum. So let's revisit the polynomial that we just looked at. F of x equals 3x to the fourth minus 4x cubed minus 12x squared plus 5. In the first example, we determined where this function was going to be increasing and decreasing. And we came up with the fact that we found its critical numbers. We didn't technically call them that while we were doing it, but that's what we did. We took the first derivative. It was a polynomial, so it existed everywhere. And we found the places where it was equal to 0. And we came up with -1, 0, and 2. We then tested the first derivative and found that it was negative on this interval, positive here, negative here, and positive here. We did all the work for this already. So once you've done all the work to figure out where your function is increasing and decreasing, you've actually just got half a step farther to determine where does it have a local max or local min, if any. So notice at -1, which is a critical number, my first derivative changed from negative to positive. That means that my original function changed from decreasing to increasing. So guess what you're picking up at -1? You're going to get a local min. So local min at f of -1. Now, we do actually want the ordered pair. Okay, this tells me where the local minimum occurs at an x value of -1, but it doesn't tell me what the local minimum is. So we need to know how low it goes. So we're going to plug in -1, but be careful. You're plugging -1 into the original function. We're looking for a point on the original function that is a minimum. So that's why we're plugging it into f, not the derivative. So we're going to take 3 times -1 to the fourth minus 4 times -1 cubed minus 12 times -1 squared plus 5. And when we get done with that calculation, we get 0. Notice we have another local minimum because we're looking for where our derivative changes from negative to positive. That happens again at 2. The derivative changed from negative to positive, which means my graph changed from decreasing to increasing. So we get a second local minimum, that's an n, at f of 2. And again, we're going to find the y value as well. So that's 3 times 2 to the fourth minus 4 times 2 cubed minus 12 times 2 squared plus 5. And when we get done with that calculation, we get -27. Notice here at 0, the derivative changed from positive to negative, which means that the original function just changed from increasing to decreasing. So there we're going to pick up a local maximum. Okay, and that'll be at f of 0. This one's a lot easier to calculate. You just zero out everything that has an x, and it leaves you with 5. So once you've determined where your original function is increasing and decreasing, we've got the local maxes and mins. We just have to kind of state them. Let's take a look at another example. Find the local maximums and local minimums for f of x equals x plus 2 sine x on the interval from 0 to 2 pi. Okay? So for local maxes and local mins, we need to find our first derivative and identify the critical numbers. So f prime of x, the derivative of f at x, the derivative of x is 1. We leave the constant out, and the derivative of sine x is cosine x. So we notice that this particular derivative exists everywhere. Cosine's domain exists everywhere. Cosine's domain is all real numbers. So we don't worry about picking up critical numbers from where it doesn't exist. So we do pick up critical numbers from where it equals 0. So the derivative equals 0 when 1 plus 2 cosine x equals 0, which says that cosine x, when we subtract the 1 and divide by 2, is going to be equal to -1/2. Now this is where your unit circle becomes extremely important. And please keep in mind that when you work with assessments in this class, you do not have a unit circle cheat sheet. Okay? You have to know the cosine of what angle gives you -1/2. And in this interval, that's going to be two of them. We're going to look at 2 pi over 3, and we're going to look at 4 pi over 3. So that's my critical numbers for my function. What I need to do is test those around those critical numbers to determine where this derivative is going to be positive and where it's going to be negative. Now this number line is going to look a little bit different because it doesn't go -infinity to infinity. It only goes 0 to 2 pi based on my interval. So we have 0, we're going to have 2 pi over 3, and we're going to have 4 pi over 3. And we want to pick test values in between these numbers to plug into the first derivative to figure out whether it's positive or negative. If you're having trouble visualizing what kind of test values to pick up, keep in mind that 2 pi over 3 is on your unit circle is sitting over here. This is your theta equals 2 pi over 3, and that your angle of 4 pi over 3 is actually sitting down here in your third quadrant. This is your theta equals 4 pi over 3. So in between an angle of 0, which is your initial side on your unit circle, and 2 pi over 3, which is the red angle, you can pick any angle you want in here, but I highly suggest one that comes out nice, like pi over 2. Okay? So if you look at the derivative with pi over 2 as a test value, okay, we'll get 1 plus 2 times the cosine of pi over 2. Well, the cosine of pi over 2 is going to be 0. So what we end up with is 1. And less important than the actual value, we end up with a positive number. Okay? I then need a test value to try in between 2 pi over 3 and 4 pi over 3. So that's in between the red terminal side and the blue terminal side. And again, you can pick anything you like, but I'm going to go with pi because that's a nicer angle to deal with. So the derivative with pi as a test value, when we plug that in, we get 1 plus 2 times the cosine of pi. The cosine at pi is going to be -1. -1 times 2 gives me -2, plus 1 is still a negative number. So in between 2 pi over 3 and 4 pi over 3, my derivative comes out negative. One more. In between 4 pi over 3 and 2 pi. So that's in between the blue terminal side and the 2 pi angle. So that's in here. I'm going to pick 3 pi over 2 as the nicest one that I see. So the derivative with 3 pi over 2 as a test value. When we plug that in, we get 1 plus 2 times the cosine of 3 pi over 2. And again, cosine at 3 pi over 2 is going to zero out, leaving me with a positive number. So we know our first derivative is positive in between 0 and 2 pi over 3. It's negative in between 2 pi over 3 and 4 pi over 3. And it's positive again between 4 pi over 3 and 2 pi. Notice your first derivative changes sign from positive to negative at 2 pi over 3. That means your original function goes from increasing to decreasing. You're going to pick up a local max. So we get a local max at f of 2 pi over 3. So again, we're not going to plug 2 pi over 3 into the derivative this time. This time we're looking for a point on the original function. So we plug it into f of x. So that's going to be 2 pi over 3 in place of x plus 2 times the sine of 2 pi over 3. And when we calculate that, that's 2 pi over 3. And then the sine of 2 pi over 3 is square root of 3 over 2. So when you multiply that by 2, it just ends up being square root of 3. So that's your local max. And then back to the number line. We notice that our first derivative changes sign from negative to positive, which means the original function goes from decreasing to increasing, which means you're going to pick up a local min. So we get a local min at f of 4 pi over 3. And again, we're plugging into the original function. So that's going to be 4 pi over 3 plus 2 times the sine of 4 pi over 3. So we get 4 pi over 3. And then the sine at 4 pi over 3 is negative square root of 3 over 2. So that's going to, once you cancel the 2's, is going to be minus the square root of 3. And this is how you want to leave your answers. You don't want to pull out a calculator and give a decimal representation. You want exact values for these local maxes and local mins. So being able to describe a curve as increasing or decreasing is an excellent way to help kind of categorize and understand what's going on with your curve. But the problem that we're going to run into is just because you have a graph or a curve that's increasing or it happens to be decreasing, it can still look different. I mean, this is an increasing function, but so is this. And they clearly look very different. This is a decreasing function, but so is this. And they have different looks. So what we'd like is another way to kind of help categorize some of this or help describe what's going on in these curves. So what we came up with is something referred to as concavity. If the graph of a function f lies above all of its tangents on an interval, then we refer to it as concave up on that interval. Alternatively, if the graph of the function lies below all of its tangents on an interval, then it's concave down on that interval. So here's what we mean by that. If I take each of these increasing functions and I start looking at the tangent lines, notice this one has a tangent line here at this point, here at this point, here at this point. Notice the function is always above its tangent lines. So this particular one is considered concave up. Now we often abbreviate that as CU, concave up. As opposed to this increasing function. Notice if I start drawing its tangent lines, let's say here, and here, and here, the function always lies below its tangent lines, as far as I have it drawn. So this one would be considered a concave down, a CD. Take a look at this decreasing function. Visualize where the tangents are going to be. Are they going to be above the function or below the function? For this particular one, the function is going to be above all of its tangents. So this one would be considered concave up. Here, the function is below all of its tangents, so this will be considered concave down. So another way to describe this would be if you were looking at a graph and it were, let's say, raining from above. If that rain were actually going to pool into your graph, it's considered concave up. If it were raining and it would hit your graph and then slide off, that's considered concave down. So if it holds water, it's concave up. If the water will slide off, it's concave down. So let's take a look at a graphical example. Here's a graph that I've drawn, and we're not going to get specific about the intervals. Notice I haven't even given you any x values, but let's talk about where this graph is concave up and where it's concave down. In the beginning, notice it starts off as concave down. So I'll write CD right here. And it's concave down, and it continues to be concave down, and notice here it's still concave down. Yes, this is going to be a local maximum, but this is still concave down on this side. If you draw in the tangent lines, the function is below its tangent lines. Now by the time we get over to this area though, it's definitely switched to concave up. So it changes from concave down to concave up somewhere right about here, give or take. And it switches to concave up. And it stays concave up until right about, let's say, here. This is a little bit-ish, but right about there it's going to switch. And it is now concave down. Concave down, and then right here, this is one of those sharp changes in direction. It switches, and all of a sudden it becomes concave up. And it's concave up, concave up. Now, don't let this sharp change in direction fool you. It's concave up on the left side of this cusp and on the right side of this cusp. So it doesn't switch until right about, let's say, here. Oops. right about here. So it's still concave up here, and then it switches to concave down. So visually, that's what we mean by concave up and concave down. Now, all of these points where we're switching from concave up to concave down, or vice versa, those points have a specific name. A point P on a curve is called an inflection point, or a point of inflection, which, by the way, you will sometimes see abbreviated as IP. If f is continuous there, and the curve changes from either concave up to concave down, or vice versa there, and it doesn't matter which way it switches. It's called a point of inflection or an inflection point regardless. So what we'd like is the ability to determine when a graph will be concave up and when it will be concave down, just like we now have the ability to tell when it's increasing and when it's decreasing. To that end, we have the concavity test. So to determine concavity, we really need to find where the derivative is increasing or decreasing. And here's what I mean by that. Let's say we look at this graph compared to this graph. These are both increasing curves. This one is concave down. This one is concave up. Notice that if I look at a couple of tangent lines, let's say I look at this one and this one. Both of these are positively sloped tangent lines to the curve. So at both points, this one and this one, we know that our first derivative is positive. Similarly, if I look at two tangent lines to this curve, let's say here and here, what you notice is that the concave down curve, the first derivative is positive here, but it's largely positive. That's a pretty steep line. This has a larger first derivative. As opposed to at this point, the first derivative is still positive, but it is a smaller first derivative. So we are talking about the rate at which that first derivative changes. It is a large first derivative going to a small first derivative. So what we're trying to examine is our first derivative increasing or is our first derivative decreasing? On the concave up one, notice it starts off as a smaller first derivative and moves to a larger first derivative. So if we're looking for where this first derivative is increasing or decreasing, we are needing to examine the derivative of the first derivative, meaning we need to look at the second derivative. So it turns out concavity is determined by a second derivative. If the second derivative of a function is greater than 0, meaning it's positive, for all x on an interval, then f is concave up on that interval. However, if your second derivative is less than 0 or negative for all x on an interval, then f is concave down on that interval. So in order to determine where a curve f is concave up or concave down, we'll be examining its second derivative and figuring out where it's positive and where it's negative. It is similar to examining the first derivative, but the information that the first derivative gives you is where your function is increasing and decreasing. Second derivative tells you where it's concave up and concave down. Let's take a look. Determine the intervals on which f of x equals 6 divided by x squared plus 3 is concave up and concave down, and find any inflection points. So in order to figure out where the curve is concave up and concave down, we need to find the second derivative. So you can use quotient rule on this, it's not incorrect, but I'm actually going to consider this instead to be 6 times x squared plus 3 to the negative 1, so that I can just apply power rule. If you use quotient rule, it's not incorrect. So the first derivative is going to be negative 1 times 6 times x squared plus 3 to the negative 2 times the derivative of our inside function, which is going to be 2x. So we're going to end up with negative 12x times x squared plus 3 to the negative 2. That's our first derivative. which, because this question only asks us about concavity, we don't actually need, other than it's our path to the second derivative. So here we go. We're going to need to use product rule. So because we have negative 12x times x squared plus 3 to the negative 2. So I'll start by taking the derivative of negative 12x, which is negative 12. We'll leave the x squared plus 3 to the negative 2 as is. And then we're going to add that to negative 12x as is. And we're going to take the derivative of x squared plus 3 to the negative 2. So that's going to be negative 2. X squared plus 3 to the negative 3 times the derivative of the inside function, which is 2x. Now this one's going to require a little bit of algebraic cleaning up. Notice that if we look at this as two terms, what they have in common is going to be a negative 12. They have x squared minus 3 to the smallest of the two exponents. Negative 3 is smaller than negative 2. So that's what we're going to factor out and open up a big set of parentheses or a bracket. When you take out the negative 12 from the first term, it has no constants left. And when you take x squared plus 3 to the negative 2 and factor out x squared plus 3 to the negative 3, you're left with x squared plus 3. That's from your first term. For the second term, I'm taking out the negative 12. I'm also taking out x squared plus 3 to the negative 3. And that should leave me with a minus 4x squared. One of the x's will be from the negative 12x, one of the x's from the 2x. So then we clean it up just a little bit more. We get negative 12 x squared plus 3 to the negative 3. When we add x squared minus 4x squared, that ends up being a negative 3x squared. I'm going to go ahead and pull that negative 3 out. That's going to leave me with a positive x squared. And when you factor out the negative 3 from the positive 3, that's going to be minus 1. So my second derivative, once I make it look pretty, ends up being 36 times x squared minus 1, which is x plus 1 times x minus 1, over x squared plus 3 cubed. So we're looking to figure out where this second derivative is positive and where it's negative. So we're going to go about this in a similar manner to when we do work with the first derivatives, but be careful. We're not actually finding critical numbers. Critical numbers are specific to first derivatives, not second derivatives. But the idea is the same. If I want to figure out where this is going to change sign, I need to examine the zeros of both the numerator and the denominator. If you take a look at the denominator, you have x squared plus 3. That will never equal 0 in the real numbers. It would take an I to make that equal to 0. So that will not be equal to 0 in real number system. For the numerator, we're looking at x equals 1 and x equals negative 1. Okay, so we're going to put those on a number line. Here's negative 1, and here's positive 1. And then same idea. We need to test inside each of our intervals, from negative infinity to negative 1, negative 1 to 1, and 1 to infinity. If we plug in something like, let's say, negative 2, notice your denominator, it's x squared plus 3, which is automatically positive, and it's being cubed. The denominator is going to be positive regardless of what you input. The 36 is going to be positive regardless of what you input. So honestly, I'm not worried about those. It's the x plus 1 times x minus 1 I need to examine. If you put in negative 2, the x plus 1 becomes negative. The x minus 1 is also negative. So you get a negative times a negative for positive. If you test a value in between negative 1 and 1, like 0, you get a positive times a negative, so that one's going to be negative. And if you test a value between 1 and infinity, like 2, you're going to get a positive times a positive. So that's positive. So we now have a description of where our second derivative is positive and where our second derivative is negative. We are then able to draw a conclusion about the original function. So that tells us that f is concave up on negative infinity to negative 1 and on 1 to infinity. That says f is concave down on negative 1 to 1. That tells me we do have places where we're switching from concave up to concave down, which means we have inflection points. So we have inflection points at f of 1 and at f of negative 1. Now because of this particular function, they're actually going to be the same because remember we're plugging into the original function, not into the second derivative now, because we're looking for points on the graph where the graph switches from concave up to concave down. And when you square the 1 and the negative 1, they're going to come out to the same value. So in either case, you get a 1 plus 3 in the denominator, so you're going to get a 4, so it's 6/4, also known as 3/2. And those are your inflection points. Let's take a look at another example. Determine the intervals on which f of x equals x squared plus 1 over x squared minus 4 is concave up and concave down, and find any inflection points. Okay? So this time when we take our derivative, we are going to go ahead and use quotient rule. So f prime of x will be, we get x squared minus 4 times the derivative of x squared plus 1, which is 2x, minus x squared plus 1 times the derivative of x squared minus 4, which is 2x, all over x squared minus 4 squared. Which there are a couple of ways to actually go about simplifying this, but if you distribute, notice you're going to get a 2x cubed here, but in the second term when you distribute, you're also going to get a 2x cubed, but it's going to be subtracted. So the 2x cubes will end up canceling. You'll end up with a negative 8x from this distribution, and you're going to end up with a negative 2x from this distribution. So we're going to end up with negative 10x over x squared minus 4 squared. That's our first derivative. Second derivative, these always take a little bit of work. Second derivative, again we're going to apply quotient rule. So it's going to be x squared minus 4 squared times the derivative of negative 10x for negative 10 minus negative 10x times the derivative of x squared minus 4 squared. That's a chain rule. So that's going to be 2 x squared minus 4 to the new power of 1 times the derivative of the inside function, which is 2x, all over your denominator squared. So that's going to be x squared minus 4 squared squared, also known as to the 4th power. So let's clean this one up. We want to treat this numerator as having two terms and take out what's common to both. They both have a negative 10 and they both have an x squared minus 4. So we'll take out negative 10 times x squared minus 4. Open up a big set of brackets. And in the first one, you'll be left with an x squared minus 4. We're taking out this negative, so you're still going to have a subtraction sign for the second term. We took out the 10, we took out the x squared minus 4. So that's going to leave me with this 2 and 2 x's, so minus 4x squared. All over x squared minus 4 to the 4th. Clean it up. Negative 10. The x squared minus 4 on the outside that we just factored out, now it can cancel the x squared minus 4 in the denominator. One of them anyway. There'll be 3 left. So we'll be left with a negative 10. Inside the big brackets, we'll clean that up to be negative 3x squared minus 4 over x squared minus 4 cubed. And then notice you've got a negative out here and 2 negatives in. So let's go ahead and, in theory, what you're doing is factoring a negative out of this to get rid of the negative in front of the 10. So that'll be 10 times 3x squared plus 4 over x squared minus 4 cubed. The algebra on this one gets a little challenging, but it's definitely doable. So now that we have a completely simplified second derivative, we're able to examine where the curve will be concave up and concave down by looking at the sign of the second derivative. So here it is rewritten. So what we need to do is figure out where this can possibly change signs. It can change signs anywhere your numerator or denominator is going to be equal to 0. Notice your numerator, 3x squared plus 4. In the real number system, that will never equal 0, so we don't have to worry about picking up any numbers from that. Down here we've got x squared minus 4, so that can change sign at both positive and negative 2. So x squared minus 4 equals 0 implies that x equals plus and minus 2. Those are the places we're going to examine. put them on a number line. So again, the intervals I'm looking at are negative infinity to negative 2, negative 2 to 2, and 2 to infinity. I need to test values inside each one of those intervals and figure out what's going on. And we want to try to work smart, not hard, on these kinds of problems. Notice your numerator is 10, which is positive, and 3x squared plus 4 is also always positive. So frankly, I'm not really worried about the sign of those factors. They're positive. I already know how to account for that. What I'm going to do is just test values into that denominator, because that can change sign. So we plug in something like, let's say, negative 3. When you square negative 3, it becomes 9. 9 minus 4 is positive. So when you cube a positive number, it always comes out positive. If you plug in something like 0, you're going to get a negative number, and when you cube a negative number, it comes out a negative. And similarly on the right, if you plug in something like 3, it's going to come out positive. So we now know where our second derivative is positive and where it's negative, which allows us to draw conclusions about the original function f. F is going to be concave up everywhere your second derivative is positive. So that is negative infinity to negative 2, and 2 to infinity. F is going to be concave down in between negative 2 and 2. So now we need to talk about inflection points. And if you're going kind of quickly and not necessarily paying attention, you may be tempted to say, look, the second derivative changes sign at negative 2 and 2, and therefore at negative 2 and 2 we must have inflection points. And here's the problem with that. Remember, the definition of inflection points was that the numbers had to be in the domain of the original function. So it's actually, I'm not looking at the second derivative anymore. I need to examine the original function, which is back here. Notice, what numbers are out of the domain of the original function? Well, 2 and negative 2 are out. Therefore, even though this does in fact change concavity at negative 2 and 2, this has no inflection points, since x equals plus and minus 2 are out of the domain. So keep an eye on that domain. It actually has a lot to do with whether or not you end up with things like inflection points, critical numbers, those kinds of things. So let's see if we can kind of start to put some of these ideas together. We're going to use intervals of increasing and decreasing, local maxes and minimums, intervals of concavity, and points of inflection to try to sketch the graph of this particular function. Now this is a function for which the graph is not obvious. You can't look at this and go, of course, it's a polynomial, it has n behavior. Both of these individually are cube root functions, and you're taking their product. So the graph of this is going to be a little more non-traditional than we're necessarily used to dealing with. Before we actually do the graph, I just want to make a quick note of something. It's not technically a part of the problem at this point, but let's talk about the domain of this function, because it's going to come into play as we want to talk about this. If you look at the domain of each of these individually, this is x to the 2/3. Keep in mind that is the cube root of x squared. The domain of a cube root function is actually all real numbers. So we're fine here. And then this is the cube root of 6 minus x, also a cube root function. So the domain for this is going to be negative infinity to infinity. If these were square roots, that would not be true. But because these are cube roots, all real numbers are acceptable. Okay? So in order to find, for example, increasing and decreasing and local max mins, the first thing I need is going to be the first derivative. So here we go. This is going to be a product rule to take the first derivative. Order is a little variable as long as you keep the right things paired with the right things. I'm going to take the derivative of x to the 2/3 first. So I'm going to get 2/3, x to the 2/3 minus 1, which is negative 1/3. Times 6 minus x to the 1/3. Here comes product rule. Plus x to the 2/3, leave that one, and then take the derivative of 6 minus x to the 1/3. So that's 1/3. times 6 minus x to the 1/3 minus 1, which is negative 2/3, times the derivative of the inside function, which is going to be negative 1. So we definitely need to clean that up because we're going to need to find critical numbers. So we're going to need to set this equal to 0 and find out where it doesn't exist. So we need to take out what is common. So what's common to the two terms, I'm going to pull out a 1/3. You could pull out a 2/3, but I'm going to pull out a 1/3. You have x to the smallest power of negative 1/3, and you have a 6 minus x to the smallest power of negative 2/3. So open up a big set of brackets. This is your GCF. When you factor out the 1/3 out of the 2/3, that's going to leave me with a 2. I've taken out the x to the negative 1/3, and now I just need to figure out what I'm left with the 6 minus x. So keep in mind that I'm taking 6 minus x to the 1/3, and I am factoring out, meaning I'm dividing out, 6 minus x to the negative 2/3. Well, that is, notice they have the same base. It's 6 minus x then to the 1/3 minus negative 2/3. Well, when you do that, you're going to add 1/3 plus 2/3, also known as 3/3, also known as 1. So you're going to end up with 6 minus x to the 1, which is just 6 minus x. That's your first term. When you take the GCF out of the second term, first of all, we are going to end up with a minus sign because of this lovely little negative 1 here. And then we took out the 1/3. This time it's the x's that are going to be a little different. I currently have x to the 2/3. I am factoring out or dividing out x to the negative 1/3. So I will get x to the 2/3 minus negative 1/3, also known as x to the 1. So there's x. And then I took out the 6 minus x to the negative 2/3. So this is what I have left. See? It's kind of complicated to look at the first time, but these clean up really nicely. So when we simplify this just a little bit more, I'm going to put my 3 in the denominator. I'm going to put this x to the negative 1/3 in the denominator, so it becomes x to the positive 1/3. 6 minus x to the negative 2/3, I'll put it down to make it 6 minus x to the positive 2/3. That's all in a denominator. This is the only thing that's going to stay in my numerator, and that's going to end up being 12 minus 2x minus x, also known as 12 minus 3x. And I see that I could factor a 3 out of these, and that if I do, it will cancel the 3 down here. So I will end up with 4 minus x over x to the 1/3 times 6 minus x to the 2/3. And that is the simplified version of my first derivative. Here it is written again. So we want to use this first derivative to figure out where is our function increasing, where is it decreasing, and where do we have local maxes and local mins. So we need to pick up our critical numbers for these. So f prime of x does not exist. Notice this has a denominator. Okay? So it's not going to exist anywhere the denominator is equal to 0. So that's going to be at x equals 0 and at x equals 6. We also are going to pick up critical numbers anywhere your derivative equals 0, and that's going to be anywhere that 4 minus x equals 0. So that's going to be when x equals 4. Should put a double header there too. Okay, so we have 3 critical numbers, 0, 6, and 4. You do want to keep a little bit of an eye on how you came up with these critical numbers, because while I'm not too concerned about the one that arose because the derivative was equal to 0, I now know for a fact that there are 2 places on this graph where my derivative doesn't exist. And remember, the only things that make derivatives not exist are discontinuities, sharp changes in direction, and vertical tangents. We know this function doesn't have any discontinuities. Think about y for a second. We looked at the domain of this function, did we not? The domain of the original function was all real numbers, and if the domain is all real numbers, it's continuous everywhere. So there's something weird going on at 0 and 6. Keep that in the back of your mind once we go to start drawing the graph. For now, we're going to put those 3 numbers on a number line. 0, 4, and 6. And we need to take a look inside each of those intervals. So negative infinity to 0, 0 to 4, 4 to 6, and 6 to infinity. So we're going to pick up test values in each one of those. I'm going to give a quick glance to see if there are any of these factors in my simplified first derivative that are going to stay positive. And 4 minus x can change sign. X to the 1/3 is the cube root of x. That could be positive or negative. 6 minus x, however, notice you are taking the cube root of that, but you're also squaring it. So that particular factor, that's going to stay positive regardless. So when I examine the signs of these, I already know that factor by definition has to be positive. So I'm going to keep that in the back of my mind. That's positive. So let me pick some test values. Let me pick, let's say, -1. 4 minus -1 is positive, and the cube root of -1 is negative. So that means overall, for negative infinity to 0, I'm going to get a negative interval. If I plug in something in between 0 and 4, like 1, I'm going to get a positive in the numerator and a positive down here in the denominator. So that interval is going to be positive. Between 4 and 6, if I do 5, I'm going to get a negative up in the numerator and a positive down in the denominator. So that interval is going to be negative. And then finally, if I plug in something like 7, I've got a negative in the numerator and a positive here. So that interval is also going to be negative. Remember, I warned you, they don't always alternate. Okay? So that tells me the sign of my first derivative, which I can in turn use to interpret whether my function is increasing or decreasing. F is increasing anywhere my first derivative is positive. So that's going to be on 0 to 4. F is decreasing where my first derivative is negative. So that's going to be from negative infinity to 0. And now you need to think about this for a second. You have a choice to make when you see these two intervals next to each other and the first derivative does not change sign. You need to choose. You're either going to write this as 4 to 6 and 6 to infinity, or you're going to write this as 4 to infinity, and only one of them is correct. So how do you know which one you're supposed to do? It depends on whether that number 6 is in the domain of the original function, because keep in mind what it is you're saying if you say 4 to infinity. If you say your function is decreasing from 4 to infinity, you're implying it exists from 4 to infinity. Whereas if you say it is decreasing from 4 to 6 and 6 to infinity, you're saying it's decreasing everywhere except 6, meaning 6 would be out of the domain. So, because we've already examined the domain of this function, we're able to say this function exists at 6. So the answer is you should be writing it as 4 to infinity in this particular case. There will be cases where you need to split this up and write it as 4 to 6 and 6 to infinity, just not for this particular function. There's the correct version. So from the first derivative, we're also going to be able to determine where we have any local maxes or local mins. Notice that my derivative changes from negative to positive at 0, which means the original function goes from decreasing to increasing. So at 0, we're going to pick up a local min. Local min at f of 0. Remember, you're not plugging 0 into the derivative to find the local min. In fact, if you tried, you'd end up with an undefined function. To identify where your local min occurs, you're looking at the original function. That's that one. The x squared to, the x to the 2/3 times 6 minus x to the 1/3. When you plug 0 into that function, you get 0. The other place we're going to see something happening is at 4. Notice the derivative changes from positive to negative, which means the original function goes from increasing to decreasing. So we're going to pick up a local max at f of 4. And when you plug 4 back into that original function, you're going to get 4 to the 2/3 times 2 to the 1/3, which if you manipulate that around, things like changing 4 to 2 squared and combining all of your exponents, you're going to end up with 2 to the 5/3. If you want to good indicator of whether or not you remember your exponential rules. Verify that this is in fact true. And normally I'd stop right here, but I know I'm going to end up sketching a graph of this because that's what the directions asked me to do. So in order to get this ordered pair on a graph, I'm going to need to know about what 2 to the 5/3 is. So if you get a decimal approximation for that, it's about 3.17. Okay, so I'll use that once I actually sketch the graph of this. So now that we've identified where our curve is going to be increasing and decreasing and its local maxes and mins, we want to talk about its concavity. And in order to do that, we would need the second derivative. But if you recall, that first derivative took us quite a while as it was. So I have actually already calculated the second derivative for you. Again, if you want some good practice at making sure you know how to use all the differentiation rules and how to simplify these algebraically, feel free to verify. But for now, take my word for it, the second derivative is -8 divided by 4, x to the 4/3 times 6 minus x to the 5/3. And I'm going to rewrite the original function here because I don't want to have to keep going back and forth between that and 2 slides ago. So the original function was x to the 2/3, 6 minus x to the 1/3. Okay? So once we already have the second derivative, we just need to examine where is this going to be positive and where is it going to be negative. And that's going to inform us for the concavity of our original curve. So we need to determine the numbers at which our second derivative can change sign. That'll be anywhere the numerator or the denominator changes sign. The numerator is actually a nice set number. It's a negative number, so that is going to have an effect on us, but it's not going to change sign. It's always going to be negative. The denominator can change signs when x to the 4/3 equals 0, also known as when x equals 0, and when 6 minus x to the 5/3 equals 0, also known when x equals 6. So 2 places that this particular second derivative can change signs. So we're going to examine what's going on between -infinity to 0, 0 to 6, and 6 to infinity. So we already know the numerator is negative. And again, I'm going to look for factors that I already know the sign that they're going to turn out. So take a look at that x to the 4/3. Keep in mind that is the cube root of x to the 4th power, which means since you're taking it to the 4th power, that's always going to stay positive. I'm not going to bother testing that. That factor is positive regardless of what's going on. So really the only thing that can change sign is 6 minus x. And frankly, the only place that can change sign is at 6. So I've already kind of informed myself this isn't going to change sign at 0. But we'll go ahead and test some values to double check it. If we plug in something like -1, again, I'm only plugging it into this factor. 6 minus -1 ends up being a positive number, so we get a positive here, which says that overall this interval ends up being negative. If you plug in something like 1, again, 6 minus 1, positive. So sure enough, it's not changing sign at 0. That's because that one has an even power on it up there. When you plug in something like 7, you're going to get 6 minus 7. You're going to get a negative number in this factor. So that one's going to become negative. So that particular interval ends up being positive. So these are the signs of my second derivative, which tell me the concavity of my original function. So f is going to be concave up anywhere my second derivative is positive, so that's 6 to infinity. And then f is going to be concave down anywhere my second derivative is negative. And again, we're going to have to make that choice again. I should either describe this as -infinity to 6 or -infinity to 0 and 0 to 6. Only one of them is correct, and the way you choose is by deciding is 0 in the domain of the original function, not of the second derivative, of the original function. That's why I wrote it up here. And we discussed the domain of the original function. It's all real numbers. So I am going to include the 0. So we're going to say -infinity to 0. So I want to take a look at where we're changing concavities, which is at 6. Verify that 6 is in fact in the domain. It is. Domain's all real numbers. So this function does have an inflection point at f of 6. To get the y value for it, we plug 6 into f, into the original function. And that actually comes out nice because 6 minus 6 is 0. It zeroes out this factor. So f of 6 should come out to be 0. So let's put all of this together and sketch the graph. So on this slide, I've kind of condensed the information that we've discovered over the past few slides because I didn't want to have to go back and forth. So things like where we found a local minimum, where we found a local maximum, our interval of increasing and decreasing, intervals of concavity, and our inflection point. And we're going to use all of that to sketch the graph. So let me get some axes on here. And I'm actually going to draw this graph twice because sometimes it can be a little overwhelming to try and incorporate all of this information at the same time. So usually to kind of circumvent that, if I'm unsure about what a graph is going to look like, I'll just deal with the increasing and decreasing first, and then I'll come back for the concavity. So I'm just going to graph the increasing, decreasing parts to get a basic idea of what the graph looks like, and then I'll redo it again to incorporate concavity. So for example, I know I have a local min at 0, 0. So let me get that on here. We have a local max at f of 4 at about 3.17, so yeah, give or take. This will be a little rough. We know it is increasing from 0 to 4. So here, my graph should be increasing. And then it's decreasing from negative infinity to 0, so here. And then again from 4 to infinity. So essentially it's going to do down, up, down. I also need to make sure I have an inflection point at f of 6 equals 0. So not only do I know that this is an inflection point, I also know it's a point on my curve. So it should go down to 0, 0, up to 4, 3.17, down to 6, 0, and then continue down. Okay, so I've got an idea of what the increasing, decreasing part of this looks like. Once I have that, then I go ahead and worry about the concavity. So let me erase this. I am going to leave the points though because those are on there. We also know that this is supposed to be concave down from negative infinity to 6. So everywhere to the left of this point, this graph is supposed to be concave down. Now that's going to be a little weird given that we have a local minimum here. I mean, we're going to come in and we're decreasing concave down, and then we're supposed to pick up a local minimum and yet still switch to increasing and still be concave down. That's a little weird at first, right? Until you remember, how did we get this particular critical number? That's where our derivative didn't exist. Remember, we said there was going to be something very strange going on at 0 because the derivative doesn't exist there. We knew it wasn't going to be a discontinuity because the domain of this function is all real numbers, so it's continuous everywhere. So the other two options for what causes a derivative not to exist is either a sharp change in direction or a vertical tangent. The fact that I have a local minimum that is concave down on both sides indicates you have a sharp change in direction at that point. So that's how we can use the derivatives to figure out that we actually have a cusp here at 0, 0. So we continue on, increasing but concave down. And then we end up with a local max. So here we switch to decreasing. Pardon me, I'm trying to connect these nicely. This isn't a sharp change in direction. I'm trying to connect these nicely. And we know it stays concave down, and then it's got a point of inflection. I'm trying to draw it in there nicely. At 6, 0. And then it is decreasing but concave up the rest of the way. This isn't supposed to be there. Sorry, my drawing skills are not excellent with this bamboo pad. So the other thing you want to keep in mind though, remember 0 was not the only place that our derivative didn't exist. The derivative also didn't exist at 6. Now based on the information that we've got about local maximums and minimums and concavities, we know this is not a sharp change in direction. We also know it's not a discontinuity because of the fact that the domain is all real numbers. So if it's not a discontinuity and it's not a sharp change in direction, what's the only other possibility for the reason this derivative didn't exist at 6? Well, it's got to have a vertical tangent. That's the only thing that's left. So when we draw this portion of the graph, we actually need to draw it almost as a vertical function right there exactly at 6. So let me redraw it with that information included. Bear with me, I'm going to try it. Here we go, and almost vertical, but also making sure we still keep it as an inflection point. And then from there, it should stay decreasing and concave up for the rest of its graph. And that's what we've got. So even though this is an extremely non-traditional graph compared to what you tend to see in pre-calculus, we're able to extract all of this information simply by looking at the first and second derivatives of the function. Let's do one more example where we're going to sketch a graph of a function that meets the following conditions. Okay, so here they are. We've got f of 0 equals 0, f of 2 equals 3, and f of 4 equals 6. What kind of information does that tell me about the graph of my function? Well, those are three ordered pairs. So let me get some axes on here. So those three ordered pairs will be 0, 0, 2, 3, and 4, 6. So that's the first condition met. The second condition says that the derivative at 0 and the derivative at 4 are both equal to 0. So that means that 0 and 4 are both critical numbers. They are our potential local maximums and local minimums. To figure out which we might be looking at, we examine the next two conditions. This one says that the first derivative is positive for all x in between 0 and 4. So in between 0 and 4, if the first derivative is positive, that means that my function must be increasing. So on my graph, that means, remember I'm going to resketch this in just a moment, I should be increasing from 0 to 4, up this direction. The next one says that my first derivative is less than 0. My first derivative is negative for any x smaller than 0 and any x greater than 4. So if the first derivative is negative, that tells me that my original function is decreasing. So on this side of 0, we should get a decreasing function, and on this side of 4, we should get a decreasing function. So we kind of have the idea of where this is going up and where it's going down. We've got decreasing, increasing, decreasing. Then we need to come back and discuss what the next two tell us. This one says the second derivative is positive for all x less than 2. So if the second derivative is positive, that tells me that the original curve, f, must be concave up for all x less than 2. So remember, it was going to be decreasing here, but now we know it's also concave up. It's going to change to increasing, but remain concave up here. And then at 2, it stops being concave up. The last condition says that the second derivative is less than 0, meaning the original function is concave down for all x greater than 2. So it's still an increasing function, but now it switches to concave down. And then at 4, we switch from increasing to decreasing. This is a curve that meets all of the conditions on the left. And that is just some of what we can determine about a function based on its first and second derivatives.